We're going to start chapter 9 today, and the only problems or lecture notes that I really have for chapter 9 is the stuff that I've given you here on these problems. Here on this first page are going to be the chapter 9 stuff that we're going to cover, and then on the back page are the chapter 10 stuff that we're going to cover, but we're not going to talk about the chapter 10 stuff until next time. So for chapter 9 is actually extremely similar to what we did in chapter 8. Both of them are hypothesis testing chapters. The difference is that chapter 8, we just made one hypothesis, a null and alternative hypothesis. But then what we ended up doing was we just went out and took one sample in order to test that hypothesis, right? We used that sample statistic, x bar or p hat, to test our hypothesis. What we're doing now differently in chapter 9 is, instead of going out and taking one sample, we're going to go out and take two samples in order to answer some kind of hypothesis. So the overarching picture for chapter 9 is this. Think of a situation where it would be necessary for you to answer some kind of question where just taking one sample isn't sufficient, right? So the examples that we covered last class for the previous chapter was, if you think back to the first example that we did, the pastry example, right? We said, hey, some bakery is producing these pastries, and these pastries are supposed to have 8 grams of fat on average, and you wanted to test to see whether or not the factory was working correctly, right? Then we decided that we had these two cutoffs, and I don't know if you remember, but it's like between 7.89 grams of fat, 8.11 grams of fat. And we went out and we took a sample, and we saw that if that sample average would have been between those two cutoffs, between our critical values, we wouldn't have rejected our hypothesis. But if it was in our rejection region, we would have. So that was just one situation where we could take one sample and we could answer our hypothesis. But suppose that we had a scenario that was this. Suppose that the department chair wanted to see how well my students are doing in statistics. So the department chair comes into this class unannounced, right, without me knowing it, and goes, hey, Michael, I want to see how your students are doing. I want them to take this test just to see, how well you're teaching them. So he gives everybody in here a statistics test, right? And, of course, you guys ace it, right? So you guys ace the statistics test, right? Of course. So that, you guys ace this test, the department chair goes back, he grades these tests, and he's just like, well, these scores are just a little bit too high. I wonder if they were cheating there. So again, unannounced, he comes back to class, gives you guys another exam, and of course on this other exam, you ace it again, right? So there would be a scenario where he would then go, all right, well, I've tested this thing twice, I'm going to say that this is completely good to go, right? That's one example where somebody might decide to take two samples, right? The first test was one sample of you all, and the second test is another sample. It could be like to double check, right? Does anybody in here have kids? Right? Yeah, I have kids, right? One of the things that, so one of my babies was recently sick, so I went to the doctor. Yeah, it kind of sucked, right? Whenever you have a kid that's sick. So I go to the doctor, and she had a really high fever, and I was like, so I want to do the flu test, right? So they do the flu test, and it comes back negative. So I was like, oh, that's great. They're like, oh, it's just a common cold, right? 2 days later, her temperature went away, so I was happy again. She was happy again. But then a couple days after that, her temperature came back. And I was like, oh, that's not good, right? Like, temperatures aren't supposed to go away and come back. So, of course, I took her to the doctor again. And I was like, so how do we know it's not the flu? And they're like, we have no idea. So I did the flu test again, right? But there's another situation where it's just like one test wasn't good enough. I wanted to do a second test, right? So you can think of that as a scenario where you're not taking one sample, but you're taking two samples of something. That's exactly the situation that we're doing in chapter 9. So whenever you think of a scenario where it's not just sufficient to just take one sample, but instead you want to take two samples, well, that's what we're talking about in chapter 9. Other than that, almost everything else that we're going to do is exactly the same that we did in chapter 8. We're still testing a claim, so we're still going to start off by writing our null and alternative hypotheses. We're still going to draw a picture. We're still going to determine if we're using Z's or T's. Still going to look at our critical values and our test statistics, and then we're going to give our conclusion. Those 6 steps that we've always been doing are going to be the exact same 6 steps. The only thing that's a little bit different are the formulas. And that's why I gave you all this formula sheet right here. So let's talk about this formula sheet. First off, let's go to the front page of the formula sheet because we didn't talk about this formula sheet last class. So let's take a look at it. If you go to the front page, the super descriptive thing at the top says formula sheet, right? But then here, if you start looking at some of these things, here you have X bar, right? X bar is simply just our sample average. So this is now going back to like chapter 2 when we first started talking about stuff. As is our sample standard deviation. Here's one of the formulas for our sample standard deviation. Here are some of the Z formulas that we've used throughout the semester. So most of this stuff right here is chapter 2. For probability, these are some of the probability things that we looked at for chapter 3. Right? So here are some of the formulas for chapter 3. Discrete random variables, this is getting into a little bit of chapter 4 now, where here we're not just looking at an average, but we're looking at an expected value, so that's why we have these probabilities associated with the 2. And the binomial distribution is also something that we saw in chapter 4. Then for sampling distributions here, this is chapter 6 type stuff, and here for the first time is when we're introducing proportions, right, where we have P and P hat. And here we have confidence intervals, so here we're getting into a little bit of chapter 7 for the minimum sample size formulas for chapter 7. You're going to get this on the final exam. You're also going to get this on your last exam. Yep. So the portion that, if you flip over to the back page now, once you get to the back page, it seems a lot more cluttered than the front page was. But if you take a close look at some of the stuff, if we look at like this top box right here, this should look really, really, really familiar to you. If you look at the first stuff that we're asking, here we're looking, okay, n is greater than or equal to 30, but here n is less than 30. Right here we're looking, if we have n being greater than or equal to 30, either we know sigma or we don't know sigma. Same thing if n is strictly less than 30, either we know sigma or we don't know sigma. So what do these two things look like? What is that coming from? It's like our chapter 7 stuff, right? It's our first 2 questions that we always started asking ourselves in chapter 7. Is n greater than or equal to 30 and is sigma no? Right? Then we did those 2 questions as the first 2 questions in chapter 7. And in chapter 8, we just wrote our hypothesis and drew the pictures first. But we still got to these 2 questions, right? So here in chapter 7, we were doing confidence intervals. And here are the confidence intervals formula that we would end up coming up with. If n was greater than or equal to 30, we always use z values. If sigma is known, we also always use z values. The only time that we didn't use a z value, when we use a t value, is whenever we had a sample size that was less than 30 and that sigma wasn't known. Right? You guys seen the stuff on here from chapter 7? Well, here, in this column right here, they're including some of the stuff from chapter 8. So this is kind of like a chapter 8 column. Because in chapter 8, we started talking about our test statistics. Right? Our test statistics. Here, technically speaking, since we're making z values and t values from our test statistics, technically speaking, these are standardized test statistics. But like I said in the past, like sometimes the verbiage is a little bit loose, where they refer to them as test statistics, but they should be saying standardized test statistics. All right. And then again, whenever we were using t-values, the way that we found t-values on our table, one of the things that we had to know were our degrees of freedom. So therefore, the only thing that's going to have degrees of freedom on this table right here is whenever we're using t-values. You guys see this from chapter 7 and part of what we've done in chapter 8? All right. Well, here, we're no longer dealing with the means. We're starting to deal with proportions. But what is this thing right here? What is this right here talking about? if it's a large or small sample, right? Exactly. Here we're taking p hat, we're adding and subtracting that, and if that is contained in the interval from 0 to 1, then we're going to say it's a large sample, and if it's not between 0 and 1, then it's not a large sample, it's a small sample. But again, if we were trying to create some kind of confidence interval for proportions, if it was a large sample, the only formula that we had ever was this right here. So we saw this in chapter 7. And again in chapter 8, if we had a large sample, if we needed a test statistic, again this is our test statistic column, if we needed a test statistic, we were just using this formula right here. So we've seen all this stuff before. Now what's going to happen is you're going to get a whole bunch of new formulas in chapter 8 and chapter 9. And this is going to, at first, look super complicated, right? You're going to be like, oh my gosh, look at all these symbols. Like, what the heck does all this stuff mean? Two things about that. As we go through this, you're going to actually see that it's relatively straightforward. And the second thing is even if it does still look a little bit complicated, you're going to have this formula sheet so you can be able to use this as a crutch, right? So before asking you guys to remember this stuff, I didn't think that was too much. But now when we're going through all these formulas in 2 chapters, that's starting to be a little bit ridiculous to ask you guys to remember this. So that's why you guys are going to get the formula sheet. But let's take a look at this right here. Just like we went through these boxes up here, let's take a look at these things right here. These boxes. Because these boxes right here, these are your chapter 9 formulas. Technically speaking, this one down here is chapter 9 as well. For proportions. However, on the past common final exams, especially those common final exams over like the last 5 or 7 years or so, very rarely make use of confidence intervals for two-sample hypothesis testing for proportions. So if you don't really understand or spend a whole lot of time on this last formula right here, this last set of formulas, you're really not going to get dinged at all. So let's talk about these 2 sets of things right here. We have independent samples, and we also have, paired samples. So let's talk about the difference between independent samples and paired samples. The difference between independent samples and paired samples is basically what chapter 9 boils down to. So independent samples, you can think of going to one group, taking a sample, and then going to a second group and taking a sample, where those 2 groups that you're taking samples from are completely different, right? Again, remember that all of chapter 9 we're taking 2 samples. Independent samples say that you go to 2 different groups, whereas paired samples say that you go to the same group twice. So what we're going to do in chapter 9 is we're always going to start off by asking ourselves the question of, are we going to the same group twice, or are we going to 2 separate groups and taking a sample from each group, right? So if we backtrack and we go back to that example for, the department chair comes walking in and gives you guys an exam and stuff like that. Is that an example of an independent sample, or is that an example of a paired sample? That's paired, right? It's paired because you're going to one group, you're taking a sample from that, i.e. the first test, right? And then you're coming back to that exact same group, and you're getting a second sample, i.e. the second, right? So therefore, because you're taking 2 measurements from the same group, we're going to call that a paired sample. Now, an independent sample might be something like this. And this is really what they do with these common final exams, is they say, let's not see just how I'm doing as a teacher, but let's see how all the statistics teachers are doing. So what they're going to do is they're going to give an exam to my class, and they're also going to give the exact same exam to all the other stats classes for all the other classes, right? And then they're going to just compare to see whose classes are doing better than the other classes, right? It's really what happens with these common final exams. But in that scenario, what's happening is they're going to one class and taking one measurement, and then they're going to a completely different class and also taking that measurement, right? So that's going to be an example of an independent sample. Right? Is everybody good with that? All right. if we have independent samples, one of the first things that we want to ask ourselves is, now we're not just interested in whether one of those samples is greater than or equal to 30, but we're interested in to see whether both of those samples are greater than or equal to 30. Either they're both going to be greater than or equal to 30, or one of them is going to be less than 30, or the other one is going to be less than 30, or both of them are going to be less than 30, right? So, in order to be up here in this top box, right, up here in this top box, we have to make sure that both of the samples are greater than or equal to 30. If one of the samples or both of the samples are not greater than or equal to 30, we are not up here in this box. Right, does that make sense? All right. Well, after that, it's pretty straightforward. If we're saying that both of them are greater than or equal to 30, we're going to use this formula right here in order to either calculate out our confidence intervals, or specifically for Chapter 9, we're going to do our hypothesis testing. And if we need to, again, have a test statistic in order to test our hypothesis, we're simply going to use this formula here instead. If we have independent samples and one or both of those samples are smaller than 30, I'm just focusing on the sample size here for a minute. This consideration is also an important consideration, but usually in this class we just assume that that is true, that both of the sigmas are unknown, but assumed to be equal, and that it's coming from a normal population. Usually we don't change this characteristic down here, we just change the sample sizes. But if we have independent samples and one of those sample sizes is less than 30, we're going to use this formula right here instead. Let's take a close look at that formula right here, because inside this formula there's this thing that's called SP squared, right? S sub P squared. And technically what that stands for, and you don't need to remember this, but technically what it stands for is that's a pooled standard deviation. That's where the P comes from, pooled standard deviation. And it's squared. Well, how are we going to get this? This SP squared is this thing right here. So it's all of this formula. So the reason why they have it on its own separate line is, if they would have taken this formula and jammed it up there underneath the square root sign, it would just jack up this table, right? So what they said is, how can we make this table look neat? Let's call this thing SP squared, and then we'll write its formula on its own line. So, if we determine that we're taking samples from different groups, and both of the samples that we're taking, or one of the samples that we're taking, is less than 30, we have to do this formula. But in order to do this formula, we also have to figure out what SP squared is, so we have to do this formula as well. So we're really doing two formulas for it, right? You guys starting to see now why I'm definitely going to give you guys the formula sheet, right? Like there's a whole lot going on here. All right. Lastly, if we don't have independent samples, if we have paired samples, then we're just going to use this formula right here. And we have this thing right here called D bar, right? This thing right here, D bar. D bar is the average difference between the pairs, right? Let's talk about it here for a second. A paired sample simply just means that you go to one group twice, right? Is everybody good with that? Suppose that it's this class, right? Like the department chair comes walking in and stuff. If they come in here and give you all a test, and then they come in here and give you all a test again, that's a paired sample. One of the things that we can do is we can see how did you perform differently on the second test as to the first test. Maybe on the first test you got a 95%, and on the second test you got a 93%, right? There we want to see that your percentage went down by 2 percentage points, right? That's your difference from test number 1 to test number 2, right? But maybe my difference from test number 1 to 2, maybe I got like a 75%, and then I got like a 68%. So my difference is now 7. Right? Is everybody good with that? If we take everybody's difference between test number 1 and test number 2, and we find that the average difference for everybody between those two tests that's what this D bar is. Right, is everybody good with that? That's what D bar is. So, in order to do this paired sample, that's why it's important that we can only do it for a paired, because we're going to the same group twice, so we're going to have pairs of measurements for everybody. Well, then we can find the differences of those pairs for everybody, and we can also find the average of those differences. All right. If we then, lastly, I'll just mention this. If we need a test statistic, which we are to test the hypothesis, the way that we're going to find out what that test statistic is here is just to use this formula. The last thing that I'm going to say then before we get into some examples is we have this D naught stuff right here. Whenever we get D naught, anything naught, right, especially from chapter 8, where's that thing coming from? Right, if it was mu naught or p naught, where would you get that value from? Your hypothesis, right? It's just your hypothesized value. So mu naught was like your hypothesized value for the averages. Your p naught was the hypothesized value for proportions. Now what we're going to start doing is we're going to look at the differences between measurements from measurement number 1 to measurement number 2. So therefore this D naught, this capital D naught thing, is just your hypothesized value for what the differences are going to be. Right? So if somebody goes, hey, I'm going to give you a test, and I'm going to give you another test, right? I'm going to give you a chapter 7 test, and then I'm going to give you a chapter 8 test. What do you think your differences in score is going to be? If you say, I feel great about chapter 8, but not so great about chapter 7, I think I'm going to be about a letter grade difference. Well, that's your hypothesis for what your difference is going to be. That's going to be D naught. Is everybody good with that? All right. So let's stop talking a little bit about these formulas, and let's actually try to do some examples. Let's go to question number 1 on chapter 9. A study to compare the mean level of LDL cholesterol in male and female students who do not exercise regularly gave the data shown in the table, which we have below. We may assume that the populations of LDL level are normally distributed with approximately equal standard deviations. And then we have this, right? So we have both men and women in the study. We have little n, and what does little n stand for again? Or sample size. So we have 35 men and 60 women. What does X bar stand for? Our sample average, right? So here, the men's average cholesterol level is 109, and the women's average cholesterol level is 96. And then little s stands for the sample standard deviation. So here are just their respective standard deviations, right? Everybody good with how to read that table? It says construct a 90% confidence interval for the difference in mean LDL cholesterol levels between men and women. All right. It's asking us to construct a confidence interval, 90% confidence interval. So that's going to be more similar to a chapter 7 question than a chapter 8 question, right? Chapter 7 dealt with confidence interval. But let's first do this. Let's first try to identify whether or not we have independent samples or paired samples. Are we going to the same group twice? We're not, right? Once we're going to the men, and then we're going to the women, or whatever it is, vice versa. Is everybody good with it? So therefore, it's independent samples, it's not paired samples. Right? Is everybody good with that? All right. So we're dealing with independent samples. Dealing with independent samples. So we have to be up here in the independent samples. Are both samples, the sample size is greater than or equal to 30? Yep. So therefore, right here we have a sample size of 35 for men and 60 for women. So therefore, they're both greater than 30. So therefore, we're just going to use this formula right here to calculate out our confidence interval for this. Right, is everybody good with that? So let's do it. So I'm going to say that this is question number 1. Question number 1, then, the formula that we said that we were going to use is x bar 1 minus x bar 2. So I'm just copying this down from the formula sheet. Plus or minus z sub alpha divided by 2 times the square root of s1 squared over n1 plus s2 squared over n2. Is everybody good with where I'm getting this formula from? All right, so let's go ahead and plug in these numbers then. Real quick, sometimes the question that I get is, which one are we calling x bar 1 and which one are we calling x bar 2? The easy way to do these problems is this. Just start at the first group, call that group number 1, and then go down to the next group and call that group number 2. So however, like if we foreshadow what we're going to do on the next questions, here faculty would be 1 and students would be 2. Here test is going to be test 1, and here this is going to be test 2, and so on and so forth. Right? Just an easy way to do it. So here it just happens to work out that men are going to be group 1 and women are going to be group 2. That's how they make the solutions on these common final exams. So usually the solutions should work out the same way regardless of how you designate it. But sometimes the in-between steps are a little bit nicer if you designate the groups that way. So here then we're going to have for x bar 1, we're going to have 109 minus x bar 2, it's 96. Plus or minus, I'm going to skip the z sub alpha divided by 2 here for a second. Is everybody good with where I got those two numbers from? And then s1 squared, what are we going to use for s1? 31. It's going to become 31 squared. What is n1? 35. And then s2 squared is? Awesome. And then n2 is? Everybody good with these numbers so far? Then the only thing that we still need is our z value, right? So we're doing confidence intervals. So whenever we're doing confidence intervals, it's always going to be alpha divided by 2. What's our confidence level for this problem? 90%. So therefore, alpha is equal to 10%. Alpha divided by 2 is 5%. So the z value that corresponds to the alpha divided by 2 of 5% is 1.645. Everybody good with how to get 1.645? Alright, so now if we do this arithmetic, give me a second, I did this arithmetic before. No, I didn't. 13 plus or minus. Somebody help me out here. Somebody back me up on that? Good? Sweet. Alright, awesome. Alright, so there we have it. So that's our confidence interval, right? It says construct this confidence interval for cholesterol levels between men and women. And here we just constructed our confidence level, or our confidence interval. So, no, you're fine. In your calculator? So my suggestion is you always do it step by step by step, right? So if I were doing this on the calculator, I would do 31 squared, and then whatever that is, I'd divide that by 35, right? And that's going to give you some number. and then I would do 26 squared, and then divide that by 60, and that's going to give you some number. And whatever those two numbers are, I would add them together. And then after you add them together, take the square root of all of that. So then we're done with what we have underneath the square root, and then multiply whatever that is. That answer gives you by 1.645. Now that should be something that's extremely, extremely, extremely close to 10.24. Might be off in like the third decimal place. Do you get 10.24? Yeah. So we can go over it after class then, because I think it's just a calculator thing. But let me ask you this. Are you good with the formula that we're using and the numbers that we're plugging in? Alright, then we'll figure out your calculator thing a little bit later. Alright, is everybody else good with the setup for this too? Alright, so that's number 1. Let's go on to number 2. A car dealer claims that on average the age of cars owned by professors is less than the age of cars owned by students. That's shenanigans. Random samples of 40 faculty cars and 36 student cars are taken and their ages are measured. The data was shown in the following table. So for faculty, there are 40 faculty. Average age of a car is 5.9 years with a sample standard deviation of 1.6 years. Students, there were 36 students that were sampled with the average age of the car of 7.1 years and a sample standard deviation of 1.8 years. State the correct hypothesis to test the claim. Right. So I'm going to say that 2A is to state the correct hypothesis. So we're going to write down the null hypothesis and the alternative hypothesis. So let's think about this here for a second. Just like we did it before, whenever we wanted to write down our null and alternative hypotheses, we always just ask ourselves those 3 questions. The first question is there a statement which contains equality? Do we have such a statement here? Right, is everybody good that we don't have one? All right. And the second question that we ask ourselves is there a statement which does not contain equality? There is. That statement is just that less than, right? So then we know that it's going to be less than. So again, here if we're calling faculty group 1 and we're calling students group 2, then what we're saying is that the average age for group 1 is less than the average age for group 2, right? Is everybody good with that? And that has to be our alternative hypothesis, right? We're all on the same page? So our alternative hypothesis then is going to be strictly less than, and we're going to say that group 1 has to be less than group 2, right? All right. Whenever we're writing down our hypothesis, what are our hypotheses always about? Not the sample. What are our hypotheses always about? Not averages. Think way back to the first definition that we had in chapter 8 that talked about a hypothesis. It says a hypothesis is a statement about a population parameter, right? So our hypothesis has to be about a population parameter. That's why we said in chapter 8, the only symbols that we're ever going to see in chapter 8 were simply just mu and p. Those were the 2 parameters that we always just used, right? All right. Here in this question, are we talking about averages or proportions? We're talking about averages, right? The average age of these cars. So we're going to use mu again, right? Is everybody good that we should have mu in our hypothesis? Cool. So then what we've agreed on so far is this. We should have mu in here. And then we should say that it should be our alternative hypothesis because it's less than. And we're looking for group 1 being less than group 2. Right? Is everybody good with this? So what we can say then is that the average of group 1, mu 1, has to be strictly less than the average of group 2, which is mu 2. So what we're now doing differently in chapter 9 is, since we're talking about two different groups, we're talking about the averages of two different populations. So we're no longer going to just have one symbol in here for the parameter. Now we're going to have a parameter for each one of those groups. Right, does that make sense? So here, we're saying that we want group 1, the average of group 1 to be strictly less than the average of group 2. But the average that we're looking at has to be a parameter. So therefore, the parameter of group 1, which is just the average of group 1, has to be strictly less than the parameter of group 2, which is just mu of the second group. Right, is everybody good with this? Alright. So, our third question always was, what's our parameter of interest? But here we've identified already that it's the average, right? So I kind of jumped the gun on that one a little bit. But let's try to figure out what our null hypothesis is. Just like we did in chapter 8, if we have the alternative hypothesis, but we do not have the null hypothesis, we can either use the complement or we can use you guys know this. What symbol can I have up here? Right? Yeah, exactly. So this one can either be greater than or equal to, or we can have the null hypothesis be exactly equal to. So if we're given the alternative hypothesis and we're not given the null hypothesis, then here, especially for the problems in this class, and again I said that this pertains really mostly to just the problems that we do in this class, either one of these two symbols for the null hypothesis is going to lead us to the exact same conclusion. So we can use greater than or equal to, or we can use exactly equal to. It's going to give you the same answer, right? So a lot of times, and if you're following along in the textbook for this, right? I don't know how many of you in here have the textbook for this class, but if you did follow along in the textbook for this class, the textbook always uses this option right here for the examples that it does, right? It always says, if you're given this one right here, you're not given this one right here, we're going to use equals for this one.
Yeah, it almost confuses me because it's like the complement. You know, when you think about complement, you think about the opposite.
Yeah, exactly right.
So that would throw me off.
So here, the textbook always uses exactly equal to, but the common final exam, and like I said, I always take questions from the common final exam. The common final exam uses either this symbol right here or this symbol right here. But what you're never going to see, whether it's on the in-class exam or the final exam, is to say that this is going to be answer choice A and this is going to be answer choice B. They're never going to have both of these up there at the same time. But one of these two is going to be available to you. And keep in mind that either one of these two is an okay answer to choose. Right? Is everybody good with this? All right. I'm going to take it one step farther, though, right? Because how did we always write our hypotheses in this class? If you think back to chapter 8, and this is something that I pointed out in chapter 8 as well, the way that we're going to write our hypotheses is always to have the parameter and then have some math symbol, and then we're going to have some number. We always want to have it as parameter, math symbol, and then number, right? That's how we had the hypotheses in chapter 8. So, question now is how can we rewrite these hypotheses so it looks like a parameter and then a math symbol and then some number? Well, what we can do is, if we want to have some number on this side instead of these parameters, what we can do is just subtract them to the other side. So here our null hypothesis and our alternative hypothesis, again here in this case, it's just going to be mu1 minus mu2 is greater than or equal to 0. I subtracted mu2 from both sides to go from this one right here to this one right here. Right, is everybody good with that? So same thing for the alternative hypothesis. I'm going to have mu1 minus mu2 is strictly less than 0. So now what I have is I have parameter, math symbol, and then some number, just like in the same format that we've been writing them in chapter 8. Does that make sense? So, yeah. So here, are you good with how we got this set up here? All right. What we've been doing whenever we write our hypotheses in this class is we've always been writing them as a parameter. So in chapter 8, it was always something like mu, and then a math symbol, so I'll just say greater than, and then some number, and I'll just say it's equal to 7 or something like that. Right? I'm just making this stuff up. We always had parameter, and then math symbol, and some number. We want to stick to that format here, but if you look at what we have up here above, that's not how we have it. Here we have parameter, math symbol, parameter. Right? You go with that? So here, since it's math symbol, parameter, math symbol, and then another parameter, if we want this over here to be a number instead, we can just subtract mu2 from both sides, and then we'll have it in the form of parameter, math symbol, and a number. Right? You good with that? So again, if we want to do the same thing over here, since both of these are completely okay answers to have, if we want to again have it as parameter, math symbol, and then a number, we can just subtract mu2 from both sides, and we're going to get that mu1 minus mu2 is equal to 0. Or here we're going to have mu1 minus mu2 is strictly less than 0. So usually what gets people in this problem is this. There's two parameters now, and that's the first thing that we see, right? The first time that we see this. In chapter 8, it was always just one parameter. Is everybody good with why we have two mu's up here? Yep. All right. Then the second thing that gets people is that usually you want to write it like this, and writing it like this is completely okay. The answer choices that they give you, though, are very, very rarely in this format. About 10% of the time or so they're in this format. About 90% of the time they're in this format. Right? Is everybody good with how to go from this top format down to the bottom? Right. All right. Done with 2A. Stated our null and alternative hypothesis for the claim. Everybody good with that? All right. Next thing that we want to do is we want to find the value of the standardized test statistic. All right, let's do it. In question 2, are we dealing with independent samples or paired samples? Why are they independent? Two different groups, so they're independent samples. So we have independent samples. We go to our formula sheet. For independent samples, the next question that we're going to ask ourselves is, are both of the sample sizes greater than or equal to 30? Right, is everybody good that both of them are greater than or equal to 30? So therefore, we're up here again. And if we want to find our standardized test statistic, well, this again is our test statistic column. We said that we're right here. So therefore, we're going to use this formula right here to find our standardized test statistic. Right, this one right here. Is everybody good that we're going to use this one to find our standardized test statistic? All right. So let's do it. 2B. Stole my thunder on that one. All right, so I'm going to copy down this formula from the formula sheet. X bar 1 minus X bar 2 minus D naught divided by the square root of S1 squared over N1 plus S2 squared over N2. Is everybody good with where I'm getting this formula from? All right, then let's plug in some numbers. What is X bar 1 in this problem? X bar 2 is? Everybody good with where these numbers are coming from? All right. I'm going to skip D naught here for a second. I'm going to come back to D naught. Because these other two, I think, are going to be pretty straightforward. What's S1? And N1 is? S2 is? And N2 is? Everybody good with where these are coming from? All right. Then the only other thing that we still need to know is what this D naught is. But I already asked you guys where we're going to get D naught from. The naughts always come from where? Our hypothesis. What's the only number that we have up in our hypothesis? The only number that we have up here in our hypotheses is just 0. Alright, so let me tell you guys this. I have yet to see a common final question where D naught was not 0. So, theoretically, it's completely okay for D naught to not be 0, but I've never seen a question where D naught wasn't 0. So, if you're freaking out on a test, and you're just like, what is D naught? If you remember that it's 0, chances are you're going to be okay with that one. Right? Let me briefly talk about why D naught would not be 0, so at least you get to come across that there. What we're saying here in this question is that the average age of faculty cars is less than the average age of the cars of students. Right, is everybody good with that? The average age of faculty cars is less than the average age of cars of students. If it were a month less, then our statement would still be correct. If it was a year less, our statement would be correct. If it was a decade less, our statement would still be correct. Right? All that we're saying is that we want the average age of cars for faculty to be less than the average age of cars for students. But somebody could have easily have said, I think that the average age of cars for faculties is at least 2 years less than the average age of cars of students. Right? You guys see the difference between those two statements? Well, then, we're not just looking for the difference of these two things to be less than 0. What we're going to be looking for is that it's going to be less than 2. Right? Because we're saying that the average age of cars of students is at least 2 years. I'm sorry, the average age of cars for faculty is at least 2 years than that of students. Right? So, whenever they're saying that it's not just less than, but it's less than by more than a certain amount, then this is going to be something that's not just 0, it's going to be whatever that amount is. But like I said, I've yet to see a problem like that. Alright, any questions about any of this stuff so far? Then what this is going to come out to be, if I did this arithmetic correctly, is negative 3.06. Somebody else get negative 3.06? Sweet. So we have a z value of negative 3.06, which is our standardized test statistic, which is what we were looking for. Any questions about this? Right. Then if we go on to 2c, it says find the p-value of this test statistic and state your conclusion at an alpha of 0.05. So we have this standardized test statistic, and our standardized test statistic is negative 3.06. And we're trying to take this, and we're trying to find the p-value in part C. What do we do to find the p-value? Take this to the table. If you take it to the table, what's the percentage that you get? Everybody good with how to find 0.0011? Like the z, negative 3.06. If you look up that z value on the table, you should get 0.0011. Everybody good with that? Alright. Here now, in order to determine if this is our p-value, though, we still have to answer those last two questions. Right? First question is our standardized test statistic positive? No. So therefore, do we have to subtract this from 1? No. Second thing that we ask ourselves in Chapter 8 is, do we have 2 rejection regions? Here it looks a little bit weird about rejection regions because we haven't identified those 2 things yet. But, so do we have 2 rejection? Oh, I guess we did state the hypotheses. Sorry, I was still back on the previous problem. We did say the alternative hypothesis. How many rejection regions do we have? Just 1. So therefore, do we multiply this by 2? Nope. So is this our p-value? Yeah, for some reason I was still stuck on problem number 1. I don't know what just happened there. Right, is everybody good that we have one rejection region so we don't multiply this by 2? So that's our p-value. So here's our p-value. What do we compare our p-value to? Alpha. Which one is greater, our p-value or alpha? Alpha is greater. So therefore, do we reject our null hypothesis or do we not? Did we go over the hurdle? Right? And we went under the hurdle. So here, that's a little frown face. So therefore, do we reject it? Yeah. We reject the null hypothesis, and here our null hypothesis is that mu1 minus mu2 is greater than or equal to 0. Or, whatever, if we chose the other one, this one, I'm not going to write or. But here, if we had a different symbol, we could have had equal symbol in there as well. Either way, we're rejecting our null hypothesis. Is everybody good that we're rejecting it? This p is less than alpha. All right, and that's 2c. How do you guys feel about 2c? You guys see the similarities between this and chapter 8? And chapter 7, obviously, with confidence intervals? All right, so we're going to say that 2c is done. Let's just briefly take a look at number 3. It says, 6 randomly selected students took an IQ test A, and the next day they took a very similar IQ test B. The scores are shown in the table below. So here we have the 6 students. Here are their IQ tests on their respective exams, exam A and exam B. It says, let D be equal to test score A minus test score B, and denote mu D the mean of the differences. It was already calculated from above that D bar is equal to -1 and S sub D is equal to 2.19. Assume that the scores in test A and B are normally distributed. Alright, then on average, people score better on the second test than on the first test they take. State the correct null and alternative hypothesis. So that's a claim that's being made, right? On average, so we're talking about averages, people score better on the second test than the first test. So we're going to go through that. We're going to just read through this problem. We're going to do this problem next class. Is everybody good that all that we're going to do is try to write down our known alternative hypothesis? Right? Which we've done a whole lot of times. Find the standardized test statistic. In order to find the standardized test statistic, we're just going to determine which one of these things that we're going to use on this table. Which one of these things are we going to use? Well, again, we're just going to ask ourselves whether or not we're dealing with independent samples or paired samples. And this problem, is it independent samples or paired samples? Paired samples, right? Because we're going to the same 6 students twice. So for paired samples, the only formula that we can use is this formula right over here. Right, is everybody good with that? You see now why in the problem they're giving you this D bar and this S sub D and stuff that we haven't seen before? Because we need it for this formula right here. Right, is everybody good with this? And then find the rejection region, state our null, or state our claim, state our decision. So we're just going to see based off of the null and alternative that we write, where our rejection regions are. We'll go through that same process. You guys see the similarities between what we're doing here and chapter 7 and chapter 8? Alright. So we're not going to quite finish up chapter 9 today. We'll call it quits there. I think you kind of see where we're going with chapter 3. What I would like you guys to do before next class is try to do question number 3 by yourself at home. And if you're really ambitious, try to do question number 4. We'll start off next class with those 2 examples. But I think you guys see the similarities, so we'll go through those 2 questions rather quickly.